Mhm. Hi, this is Matthew Barwigan, and sorry, how
Sean,
do you want me to call you Sean? Okay, sorry, I've never
yeah,
asked, but all right,
that's all
Sean
good.
Chen.
Yeah.
Okay, all right.
And then this is our research project for Stat 512. And then as you can see, we have the PowerPoint slides. Our topic is how effective are the vaccines at reducing the number of COVID-19 cases in Indiana? And the general research question is how much linear impact do different types of vaccines have on the number of newly confirmed COVID-19 cases in Indiana? And the background for the research, basically COVID-19 emerges to prevalence in the United States in early 2020 and is eventually declared a pandemic. And companies raced to develop and manufacture a vaccine while the world took other measures to slow down the virus in the meantime. And vaccines began to be limitedly distributed in December of 2020, with everyone that's age 12 and up eligible for vaccines starting at May 10th, 2021. And even though the vaccine is available since then, not everyone has chosen to take it. And as of October 1st, 48% of Indiana's population is fully vaccinated, and 52% of the population have at least one dose. As of October 1st as well, there has been a total of 969,375 recorded COVID-19 cases in Indiana. And here's the source for our data. You can find it through the link there. And our sample size is 30, and a non-predictor ID is included to organize the data. And as you can see, the variables are as follows. We have case first, second, single, booster, Foley. All of them are of the continuous type, and as you can see, case is assigned to be Y, and first X1, second X2, single X3, booster X4, and Foley X5. And also, these data are taken from September 1st to September 30th, so in the length of a month as well. And here are the variables in detail. So the beta 1 is the daily increase in the number of first doses administered. Beta 2 is the daily increase in the number of second doses administered. Beta 3, the daily increase in the number of single dose series administered. Beta 4 is the daily increase in number of booster dose series administered. Beta 5 is the daily increase in number of fully vaccinated individuals. Those are the explanatory variables, and the response variable is the daily increase in number of confirmed COVID-19 cases. And here is our analysis of the data. As you can see on the box plot, we have possible outliers for the variable x2, x4, and x5. Especially on X4, since the booster shots have only recently been administered, so you can expect some outliers there. The variance seems fairly consistent except X3 and X4. And also on the right, you can see that the impact of X1 and X4 are significant. The R squared value is 0.4962. Adjusted R square is 0.4156. Um, and the p-value is very low, suggesting a significant impact. And you can also see the ANOVA table there as well. And then the BF test, which allows us to tell if the difference is statistically significant or not. and we can see by the result that is not statistically significant. And then the Shapiro-Wilk normality test, which allows us to tell if the residuals are follow a normal pattern or not. We can see that we reject the no, the residuals are normally distributed, meaning they're not normally distributed. And so here you can see we transform the y because we are trying to fix the issue that the residuals are not normally distributed. And we use the Box-Cox method to try to fix the normality issue. The new model using transformation uses the formula below that you can see on there, and that transforms the y. And Matthew, do you want to take over a little here?
Yeah, I can talk about once we used the lambda of 1.24 that we got from the Box-Cox transformation, we applied that to our response variable cases and used the Brown-Forsyth test and Shapiro normality test again. And we didn't get any difference in significance of these tests. The data still passed the Brown-Forsyth test, but still failed the Shapiro test. And we ran a summary and ANOVA on this transformed data set, and our squared values increased to 0.509 and adjusted R squared to 0.4304, and the p-value changed to 0.001013. We had one more predictor variable become significant, but with the transformed data still failing the Shapiro test and having issues with the normality of the residuals and the marginal increase in R squared, we determined that it is not worth it to use this transformed data, and we'll still be using our original data set. From there, we looked at the multicollinearity of our different predictor variables. Judging from the graphs here, there's a significant multicollinearity between several of our variables. And at the bottom there, we can see any values that are greater than 0.85 are cause for concern, and we have listed out there the variables which have a value greater than 0.85. And we tried running a ridge regression to fix this multicollinearity issue, but with our X5 fully vaccinated being built from X1 and X2, it was causing some issues. So once we removed X5, our multicollinearity issues went away. We have our VIFs at the bottom there, and all of them are less than 10, which is the threshold for a severe concern of multicollinearity. So once we removed X5 from our model, we were cleared to move on past multicollinearity without using the ridge regression. And then from there, we went and looked at outliers. From the plot, you can see that entries 15 and 27 were of concern with how large their influence appeared to be and how far away they were. And we used Cook's distance down there at the bottom and found the thresholds for moderate or minor and major influence, which were 0.4629 and 0.8942 respectively. And judging from our entries there, none of the influential points that are identified were either minor or major influence. Therefore, we didn't need to get rid of any of our data points, and we are cleared to continue. From there, we went and looked at for the best subset of our predictor variables. Here we look at the SSE, the CP, the AIC, the SBC, and the PRESP. With the lowest values of SSE, AIC, and SBC, the full model appears to be the best model for us, even though it doesn't have the lowest CP or PRESP. We verified this using k-fold validation, and you can see that the RMSE is lowest for the full model with all the predictor variables. It is the model that we are going to be using, and the k-fold validation means that it is the one that we should be using. So here's our model after we validated our data and made sure that we were using the best model possible. It includes all our predictor variables. It's the best because it has the lowest RMSE, and we didn't need to transform it because when we did, the transformation didn't take care of our non-normal residual problem. So we're just going to leave it how it is, and no outliers were needed to be taken out of the data set for us to be able to use it.
I can take over from
Yeah,
here.
Sean, if you want to go ahead with question one.
All right, so we had 3 research questions, and the first one asks, does being fully vaccinated have a stronger linear impact on the number of newly confirmed COVID-19 cases in Indiana than just getting the first dose of the 2-dose series? So our null hypothesis was beta 1 equals beta 5, meaning same or similar linear impact from these 2 variables. And the alternative hypothesis is beta 1 is smaller than beta 5, meaning a stronger linear impact from the 5th variable. And the second research question was, is there a difference in the level of linear impact on the number of newly confirmed COVID-19 cases in Indiana between completing a 1 series dose versus a 2 series dose? So our null hypothesis was beta 2 equals beta 3, meaning the linear impact is the same or similar. And the alternative hypothesis is beta 2 doesn't equal beta 3, meaning the linear impact is different from these 2 variables. And the third research question was, does getting a booster shot have a linear impact on the number of newly confirmed COVID-19 cases in Indiana? So the null hypothesis is beta 4 equals 0, meaning there's no linear impact. The alternative hypothesis is beta 4 doesn't equal 0, meaning there is linear impact. And our answer for the first research question, we looked at the confidence intervals for beta 1 and beta 5, exploring their impact. And we can see the confidence interval for beta 1 is 0.226 and to 0.658, and the confidence interval for beta 5 is 0.081 and 0.505. And we can observe a significant overlap between these 2 intervals. So we decide to not reject the null hypothesis for this one. And for research question number 2, we took a similar method and looked at the confidence intervals for beta 2 and beta 3. And as you can see, for beta 2, we have 0.077 to 0.558. And for beta 3, we have 1.056 to 4.326. We can observe that there is no overlap between these two intervals. So we reject the null hypothesis in favor of the alternative hypothesis. And for the final research question, we can see from the ANOVA table there that the beta 4 equals 0. The reduced model is case with first plus second plus single plus Foley. Since our p-value is 0.03214, which is smaller than the alpha value 0.05, so we reject no. The number of boosters being administered has a linear impact on the number of COVID cases. And our conclusion for this research project is that the amount of linear impact of a number of cases is roughly the same for single shots and for fully vaccination shots. There is a difference in level of linear impact on the number of cases between a one-shot dose and a two-shot dose. Number of cases of COVID linearly related to number of booster shots. And that concludes our project and also our presentation. Thank you for watching.
Great.